Yeah, but that was unexpected. I didn't know I got a boo-boo.
I haven't heard someone say
All of
boo-boo
a
in a long
sudden
time,
now
but I'm
it makes
glad that you
significantly
did
more
that.
sense.
That's adorable.
What else would you call it?
An injury.
A wound? It sounds too severe. Injury sounds just too
cut.
severe. No, I like boo.
I like the idea of a really severe injury and you call it a boo-boo.
I broke my leg, but it's just a boo-boo.
Internal bleeding. What's
Just
a
a
boo-boo?
boo-boo.
Don't worry, I'll quiet down when you start talking.
Yeah, I'm just debating what time. It's 5 past now.
Ooh, I need to
so.
pick a color. What color should I write notes in?
Pink.
Cyan.
I do have cyan, see?
I know.
But the thing is, these are too light. I think I'm gonna use a dark color. I'm gonna be boring. Just because,
At least dark blue.
yeah,
At least
I'll
make
use a
it
dark blue.
Don't be black.
Blood.
Black ink is
Just write with
terrible.
blood. So like an IV, like fountain pen. Okay,
All right, maybe we should get going. I don't know how long the slides I have are going to take, so we might still be here 3 hours from now. Hopefully not. I won't. Oh no, I won't hold you. I'm kidding, but I do.
I'm kidding, but not.
I do legitimately not know if I'll get through all my slides, or maybe I'll get through them all onto next lecture already. But yeah, welcome. Thank you all for coming. So yeah, all of you sort of, I expect have a general sense of what this is already. I just, I wanted to start off by saying that I think this is going to be a lot of fun. I've had a lot of fun already just on like the prep work for this. And I know a lot of you have been asking for this for a while, so I'm really happy to, just, be able to help out and offer you guys, sort of some discussion about radio astronomy. I think one thing I'll preface this with is I had to teach myself radio astronomy completely. And so I have no formal education. And so already the fact that we're 60 seconds into this lecture means you guys have more formal training in radio astronomy than I have. So, good job. Yeah. Oh, I guess I should say right away, I am recording the lectures. So, hopefully that doesn't bother anyone. Be professional, I guess. Whatever. So yeah, I am going to take this very casually because, I am just here to tell you guys stuff, basically. Oh,
Hello.
Oh, someone has joined. Hello.
Use these.
Hey.
Perfect timing. Just
Thanks
about
for setting this up, Cameron.
So you can see it fine. You can sort of see me. And
I can, yeah.
slide.
Yeah, it's perfect. Thank you.
Okay, I did it properly. Good job.
You did
Okay,
it.
cool. Okay, perfect timing. So I was just about to hit slide 2, which is boring. So yeah, for today, so start off with just a little bit of course logistics stuff because this has been burdened upon me as an official mini course. And then I want to start with sort of today's theme is sort of basics, sort of idea of just a little bit on the radio spectrum. And then I want to go sort of down the signal chain of a telescope, sort of how radio signals in the sky basically propagate through your telescope into something that a human being looks at. Sort of just cover the major steps in that sort of as preparation for getting into sort of the more sticky stuff, which lecture 2 is interferometry.
Yes. That's scary.
So
Hey,
yeah,
Cameron.
so syllabus. Sorry?
Hey, sorry to interrupt. Do you think you could share your screen because it actually is blurry and I can't read it? If you
Oh, is it not sharing? Oh, yeah, sorry. I didn't mean to properly share. And I know what happened. Okay. This will be fixed.
No worries.
This will be fixed. Thank you for pointing that out.
Awesome. Oh, amazing. Thank you so much. It's perfect.
Okay, that is the way it was supposed to be.
Okay, great. Thanks.
Okay. Okay, good for now. So yeah, so you've all probably seen the syllabus. The plan as it is now is I want to do 4 lectures, which are just going to be me talking about things mostly. And I do want you guys to ask lots of questions, just interrupt me. Very casual is what I want this. I've designed the lectures with the idea of trying to complement some of the existing references. Some of the really essential stuff I'm covering. I'm pulling a lot of inspiration from the Essential Radio Astronomy by Condon and Ransom, which is a really cool web resource. I've stolen a lot of their figures because I didn't want to spend time doing my own. And so I definitely encourage you to look through this if you have some time. There are some other books that I linked, which I found less helpful, but do go into more detail on certain aspects. And so I've designed to sort of cover the essentials, taking from those and trying to, simplify them and condense them a bit. And I've also tried to fill in gaps where I think they've really kind of messed up or not explained things well. So this is sort of my own take on a lot of this. And one tricky bit is I think I could probably come up with enough content for 3 full-length courses on radio astronomy. This is a single mini course, which is a third of a normal course. So I'm trying to condense things by a factor of 9. And so it is going to be a bit of a whirlwind tour. But, you know, I am happy to stop and spend a few minutes on any particular thing that grabs someone's interest, or if it's confusing. There is going to be some homework. You know, this was mandated for mini course. So I'm doing one sort of standard problem set to just sort of work through some simple problems. I'm trying to make them fun because I don't want to burden you guys with homework. And so I'm using this as an excuse to do sort of extra material that I think is interesting and sort of stuff that doesn't fit into the lectures. And so I'm hoping all of you guys, even the ones who aren't doing it for credit, will sort of take a look. The first question is designed but not yet posted. I was going to do that this week and then I got sick. So that will come in the next few days. And then I'm going to just do these as I develop them, I'll post them. And then the idea being you just turn in your answers for the people who are crediting, turn in your answers at the end of the course. And, you know, I'll give them some vague look over and say, you know, good job. And then I do have to grade the guys who are crediting, and those grades have to be approved by Rachel Friesen, who is sort of the course faculty overseer. So I should also say, if there's anything about the course, you know, that you want to comment on that you don't want to say directly to me, you can just say it directly to Rachel. Or I am trying to organize an end of course instructor survey thing for at the end of the course.
So I just have a question about the homework. So you're posting questions like every week, and then we hand them in at the end of the course?
That's the plan.
Okay.
And yeah, if you haven't gotten the impression already, I'm not being that strict about it, so do it how you want. Groups are definitely encouraged, especially like all the people who aren't doing it for credit. If you want to group up with crediting students, that way, you know, you're helping them out, and you know, you're all sort of seeing it as a group. You know, write it up however you want. You can just do standard, you know, handwritten assignment notes. You could do like a LaTeX thing. You could write a paper. You could you could give them any scientific communication I have written here. So you could create slides, give a talk, upload it to YouTube, send me the link, and I will grade that. You know, you could, you know, do any of that. The only thing I will not accept is interpretive dance. If you do interpretive dance, I will watch it, I will applaud, I will score you a 0. That is not scientific communication. But yeah, not being too fussy about the details. In addition, there's going to be one tutorial focusing around sort of data processing in CASA. So CASA is the software used to process VLA data. It's sort of the most commonly used radio astronomy reduction package. And so I want to do sort of a data processing exercise where everyone finds an interesting data set, and I haven't actually done this myself yet, so I need to set this up and try this myself before I inflict it on you guys. But ideally, you find an interesting data set, reduce it, calibrate it, image it, hopefully get a nice pretty image out, maybe do a scientific measurement. And then for the crediting students, just kind of document that process a little bit, with the emphasis on you know, what you did, what tasks and why they're essential, what parameters you used and why you chose particular values, that kind of a thing. So nothing too interesting, but this is just kind of a hands-on thing, and this is going to take the place of one of the lecture slots. Probably lecture like week 3 or week 4. Depends on how quickly I can get it actually organized. Sometime after lecture 2, which is interferometry. And so yeah, same kind of thing. Turn in some kind of a report, maybe even a Jupyter notebook. Because I think CASA can now be run in Jupyter, I think. I heard a rumor that the newest version is Jupyter compatible. So
that changes everything.
So yeah, this could be an option. We'll see. And then similarly, yeah, it's deadline 1 week after lecture. Chris made me put in a drop date, which is 3 weeks from now. And so there's a couple of people that weren't sure if they were going to audit or credit, so I will push you to make a decision before that deadline, just because I have to turn in the list of crediting students to Margaret for registration purposes. And then there's grades deadline, which is 2 weeks after the last lecture. so that you guys aren't waiting ages on grades. And so that's a week after the homework, so I'll try and make sure I get all the marking done fast, just not keep you guys waiting. And there is a course website, which this course pushed me to actually create my own website, which is something I've been putting off for years. So it's there, and it's very basic, but it basically repeats most of what I just said, and the syllabus links and all the other links. And the lectures I'll be posting there as well, for people who want to look at the PDFs afterwards. Any logistics questions? Cool. Radio astronomy. So every radio astronomy course is obliged to start with the history of radio astronomy. I could not escape this, so here it is in one slide.
Mm-hmm.
First detection of astrophysical radio emission, 1932 by Karl Jansky. First deliberate detection of astrophysical radio emission, 1937, with Grota Reber building the first first proper purpose-built radio telescope. 22-foot diameter dish shown here. From there, it just becomes an endless succession of firsts. The only one that I think is the most important is Hendrik van de Hulst, physicist, predicted the existence of the 21-centimeter hydrogen line, which is one of the most important aspects of radio astronomy, both historically and present day. And the detection of the 21-centimeter line within, I think, a year or two of that. And everything else is, well, history. So let's motivate why radio is the coolest astronomy. So let's talk about atmospheric windows. This is a plot of atmospheric opacity as a function of wavelength. So this is effectively how much light is being blocked by the Earth's atmosphere. And immediately there are two windows, right? The optical window is mostly transparent, as well as sort of some of the infrared is a bit of a mess, but you can see some infrared bands. And then this giant band here in the radio. And so these are the only two bands from which you can do ground-based astronomy. And so you can do the most with the least actual investment in space equipment in those two bands. And the radio band is about 4 orders of magnitude bigger than the optical band. And so, you know, straightforwardly, you can kind of say, well, there's clearly that much more physics we can do than with optical telescopes. It's kind of the motivation there. The radio band is basically bounded by 2 physical processes. At the long wavelength limit, it's ionospheric absorption. So the ionosphere is made of plasma. Plasma absorbs low frequency radio emission. There's basically a derivation of this in every plasma physics textbook, so I'm not going to talk about it. But the density of free electrons in the ionosphere basically sets the lower limit from what you can observe through that. And so that's basically fixed, fluctuating a bit depending on ionospheric conditions. The short wavelength limit is basically limited by water absorption bands, so molecular line absorption bands. And so you can actually push that boundary quite a bit, but basically by going above most of the water vapor. And so that's why we have ALMA on the Atacama Plateau at 12 or 14,000 feet elevation, and JCMT up on Mauna Kea is basically the same reason as the optical telescopes, get above the water. And so that lets you sort of push this boundary up into the submillimeter regime. So you get another sort of 2 orders of magnitude out of that. And then, you know, at some point, molecular lines just make it impossible. So that's about as high as you can reasonably go. So another sort of different look at the electromagnetic spectrum. This one is now flipped compared to the other one. So this is sort of frequency axis increasing and then wavelength axis running the other way. And so swapping between frequency and wavelength is a very useful skill, I guess. Different astronomers have different preferences. I work in frequency space 90% of the time. And so that's how I tend to talk, and that's how I'll probably talk throughout the course. And then you get people who just sit in wavelength space and like to talk about that. And, you know, all these old papers about talking about like the 8-centimeter band, and I have to sort of stop and think, 8 centimeters is how many gigahertz? You get used to it after some point. There are a lot of different ways of kind of subdividing it. So people who do like ham radio and stuff talk about like high frequency, very high frequency, ultra high frequency, etc. I don't ever see that in radio astronomy. You do sometimes people see people talking about different named bands by letter, like L band, S band, C band. That's a very American system. The VLA guys tend to talk about it a lot. I don't see it that much outside of it, other than, you know, the Americans kind of corrupting the terminology of the rest of the world. And so I only bother memorizing the ones that I work with. And so I know where L band is and I know where S band is, and everything else is kind of out there in frequency space somewhere. So I'm not going to recommend that you guys memorize it until you need to. So again, sort of a different look at the electromagnetic spectrum. This is the United States frequency allocation. So bandwidth is big money these days. You know, you hear about things like auctions for like cell phone bandwidth and stuff. So since the labels are too small to read, here's sort of the frequency scale. So each of these rows is a factor of 10 in frequency. And each block is how the Americans have decided that part of the spectrum should be used, color-coded by different applications. And radio astronomy is the bright yellow boxes, which are kind of difficult to see.
It's so sad.
It is very sad. So I've highlighted them with, you know, here in green, and it is a very tiny bit of the radio spectrum. And so, you know, when radio astronomy first started, this may have been okay because, you know, the instruments couldn't handle very much bandwidth. And a lot of these little blocks are set around astrophysically interesting areas like the H1 line. There's an OH line, I think, somewhere in there, things like that. But in the modern day, this is not really good enough. We want the most bandwidth to get, you know, collect the most photons, essentially. And so we basically go outside of our allowed bands, because we're only absorbing, we're not transmitting. So we're allowed. And we basically just have to put up with all of these different kinds of man-made interference. So RFI, radio frequency interference, is basically the bane of our existence. And, you know, these are some of the typical sources that we have to try to work around. And so, yeah, modern radio astronomy basically covers most of the spectrum. So the bottom, lowest frequency, and this is put down below the ionosphere, so you still use this at ground level, but you just can't see through into space. And basically everything above that limit is being used for astronomy. I went hunting for sort of frequency specs on a lot of different telescopes, and basically continuous. There's in the high frequency regime, there's a couple of gaps that I couldn't find any telescopes for. Those might be just like absorption bands, or maybe, you know, maybe there are telescopes that I didn't find. And then just for fun, I basically marked all the frequencies, parts of the frequency spectrum that I've worked in, which turns out to be more than I thought. So, you know, there's a lot of different things going on there. So this is basically the span in which we have to work with. This is 4.5 orders of magnitude in frequency.
Where's Alma?
Alma is up here, high frequency regime somewhere. I don't actually, how low does Alma go? I want to say 70, yeah, I want to say 70 gigahertz is the lowest Alma goes, but I could be wrong. Within an order of magnitude, that's the right
So it's
number.
like that middle-ish band.
So it's the bottom one.
Yeah, the
somewhere
bottom,
there.
middle. Area.
And above. I think Alma can actually go higher than this.
Oh, okay.
Doesn't Alma go up to like 900 gig, I think?
Ooh.
I don't know.
Ask
I
Jessica.
haven't worked with Alma, so.
Jessica loves Alma.
So, but,
I think so.
yeah, so this is sort of the span we have. So with that said, yeah, so the main thing for today is I wanted to cover, you know, radio telescopes from start to finish, which is a lot in one day, but we'll see how far we get, which is sort of the whole sort of signal path going from the sky through all the sort of main components in the system. Some of these are optional. Dishes are technically optional, and that's a fun topic. IF mixing, whatever that is an optional thing in some cases. Channelization and correlation can be done somewhat in either order, so I marked that kind of specially. But all of these other steps are fairly standard, I think. And some of them are not so astrophysically interesting, so I'll just cover them very, very briefly. But some of them are the kinds of things that we have to think about a lot when we're making an observation or processing an observation. I see a lot of people writing furiously, so maybe I won't advance the slide for a few seconds. Any comments so far? So starting with the sky, because there are things to be said before we even build any kind of radio telescopes, let's talk about EM waves. So I'm hoping all you guys are sort of vaguely comfortable with the sort of single monochromatic plane wave, where you just have the real component of some vector and then your usual e to the I, kx, omega t, and a phase factor. And these are transverse waves. We've sort of always working in this coordinate system where the wave is propagating along the z-axis. And so a linearly polarized wave, you just have, you know, an x and a y component. And so in principle, then you can build up an entire sky out of infinitely many such waves. You basically can add up waves of different frequencies and as a function of direction of propagation. And so in principle, this gives you the electric field, you know, at your reference position as a function of time for sort of all incoming EM radiation. Let me know if I'm skipping through slides before you finish writing, because otherwise I'm just going to keep going. I mean, the slides are going to be posted, you know, so it's up to you how you want to keep notes. So the monochromatic plane wave is not good enough for all of the analysis that I'll be discussing today. This is a slide that I've stolen from Rick Purley, who works at the NRIO in Socorro, New Mexico. He works with the VLA, and he's been there since they built the VLA. He knows more about interferometry than like the rest of us combined. And so I've stolen some of his slides from the VLA summer school from a couple of years ago. And so these are all these slides are also posted online, and I put links to them in the syllabus. And so they're a really cool resource. They have the slides from the summer school, and they also have the lectures from the summer school online. So, you know, if you're ever bored, you know, definitely take a look. But anyway, so monochromatic plane waves are not quite good enough. So for some analysis, we need to go into the quasi-monochromatic limit. And so this is basically because, as Rick pointed out, a perfectly monochromatic wave lasts forever, and it basically can't transmit any power. And so whenever we start having to think about like power and related processes in the system, we need to assign some bandwidth to our signal. And so we consider this sort of quasi-monochromatic form, where you basically say you have some signal that has some very tiny finite bandwidth around some central frequency, but you know, you keep that small, and the result is that because you have a single, you know, everything's sort of focused around a single central frequency, signal tends to basically still be sinusoidal, but that sinusoid tends to wander a little bit over time. It tends to be altered. Sometimes it'll have lower amplitude. The phase tends to shift around a bit. So you end up with this coherence time, which is basically 1 over the bandwidth. And so you can basically say within the coherence time, you have a sine wave, effectively. And then as you sort of move several coherence times, you know, into the future, suddenly your wave is not going to look the same. And so if you express your plane wave just as the straight up, you know, sinusoid, you know, you have basically 2 parameters defining your sinusoid, the amplitude and the phase parameter, and those will be effectively fixed within 1 coherence time. So you can define a wave, you know, at any particular moment with these parameters, but those parameters will evolve sort of on time scales longer than your coherence time.
So why monochromatic wave of this power?
Yeah, that's a really interesting question.
Serious question.
Is why does a purely monochromatic wave not deliver any power?
Yeah.
I think that's actually a surprisingly difficult question within sort of my own grasp of the mathematics. I think to some degree, if I go back, is in terms of this integral. So there has to be, in order for this integral to be dimensionally correct, there has to be some term here that I've lost in terms of dividing by bandwidth and dividing over solid angle. So this equation is dimensionally incorrect as I've written it. Shame on me. But there has to be some factor of the bandwidth. If you basically drop this integral, you have no, because this has to be correct. So this has to have units of electric fields, and this has to have units of electric field per bandwidth per solid angle on the sky. So if your bandwidth goes to 0, your electric field drops to 0 in some way. That's not a particularly good answer. And I'm not sure I can do a better one on the spot. I'll stash that in the back of my mind for now, I think. See if I can come up with a better explanation. So we're going to work in that approximation. Having said that, I immediately drop that and go back to the purely monochromatic approximation. So I just want to introduce the idea of Jones formalism here. So this is going to pop up once in a while in the next couple slides, because this is sort of the useful mathematical formalism that we use to describe calibration particularly. It's particularly useful. You tend not to deal with it in sort of the day-to-day of doing radio astronomy, but it's kind of nice to know just the mathematical structure of the underlying problem when you are trying to calibrate data. And the idea is you can describe your electromagnetic wave this way, but a lot of this is kind of redundant. Like if you've picked your direction of travel of your wave, you've picked your frequency, the whole sort of wave kernel of this first two terms of this exponential, is basically fixed in the sense that you know what it looks like. And so the only interesting parts of describing the wave are your direction, your polarization vector, and the phase parameter. And so you can just pull those out and you can write a vector like this. So this is a two-component vector, which is the electric field orientation and strength and your phase factor. And so this is the Jones vector for the wave. And so this is defined for any monochromatic plane wave, and it encodes all of the sort of unique properties of the wave, the amplitude, the phase, and the polarization state. And the nice thing about it is it's actually slightly more general. So this formalism is for linearly polarized waves. The Jones formalism can be extended to circularly polarized waves or elliptically polarized waves. So it's general for any polarization state. And it's intrinsically a complex vector. So you basically have 4 parameters hidden away in this 2-component vector. And those 4 parameters give you phase, amplitude, polarization state. And then if the 4th parameter only matters if you have an absolute phase reference, which is a bit of a bizarre statement to make, but I won't get too far into the details right now. But if you don't have an absolute phase reference, you can basically drop one parameter sort of arbitrary. You can just change what you reference 0 phase to and drop one parameter in that respect. And so this formalism will become really useful for describing signal processing, signal evolution.
What's the polarization states like from the equation?
So extracting the polarization state is a little bit tricky. And so, for example, if you have a linearly polarized wave, both of these have the same phase, I think, or they can be anti-phase. It's not something you can trivially extract. The polarization parameters are basically functions of these two variables. You can rewrite these to express it in terms of things like polarization angle and ellipticity if you have circular or elliptically polarized. So there are sort of sets of equations that you can express all of those variables in terms of these or vice versa. And I'm sort of skipping a lot of the polarization details because there is going to be a separate lecture on polarization. And so some of those details I'm putting off until later. And so the main takeaway is that we have this sort of 2-element complex vector as a way of describing a wave. And the reason this is useful is any linear operation on your signal just becomes a matrix multiplication. You can define any linear operation as a 2x2 complex matrix. You actually have 8 parameters. And any linear modification of the signal, you just whack on a matrix multiplication with the matrix relevant to how you're transforming the signal. And so I have a couple of slides way at the end of the lecture that kind of demonstrate how this looks, sort of once we've gone through how the signals actually do get modified by the components. And it's just a very tidy mathematical sort of notation. Things like converting between circular and linear polarization bases is just a matrix. So just as a reminder, you can describe any electromagnetic wave as either the superposition of an x-axis oscillation and a y-axis oscillation, or as a clockwise and an anti-clockwise oscillation. And so you can do everything in a basis of left and right hand circular polarizations. You can go through all of the math, all the derivations, everything works out the same, and then just do the conversion as a simple matrix operation. And so this is nice if you build an antenna that is circularly polarized. You can have a circularly polarized antenna and work through all the signal processing in that kind of circular basis. And all polarization independent effects just exist as diagonal matrices or even just like the identity matrix. And so there's some nice mathematical aspect if you dig deeply into sort of the underlying mathematics of this whole process, which is a little bit frightening. I have dug into some of the actual mathematics of interferometry expressed in Jones formalism. It's a little frightening, but it's a lot less ugly than you might expect. So I mention this now so that when it comes up later, it kind of makes a little bit more sense. Flux and intensity units. So I'm not sure, maybe you guys have seen this in terms of radiative transfer stuff. But there's sort of a number of different but related units that kind of come up. And I tend to use them wrong. I basically call everything a flux or an intensity, even when that's not what I actually mean. So for the rest of this course, whenever I talk about flux or intensity, if you think I'm using the wrong word, I want you to call me out. So I'm trying to get better about this. But the distinction is that an intensity or a specific intensity or a spectral intensity or spectral brightness, usually denoted by I, and it is the energy per time, so a power essentially, power per unit frequency, per unit collecting area of telescope, per unit solid angle on the sky. And the reason this is a good quantity to look for is it's independent of instrument because you've normalized out for collecting area, you've normalized out for bandwidth, you've normalized out for observing time, such like that. And weirdly, it is independent of distance because as something goes further away, we know energy should drop as distance squared. Angular solid angle, as it goes further away, drops as distance squared. So that cancels out. And so strictly speaking, intensity, when you measure it properly, which we don't usually do, but that's a topic for another day. Intensity is nominally independent of distance and independent of all instrumental parameters. So it's a very nice thing to use. Very commonly, if you integrate over the size, apparent size of a source, what you then get is flux density. And so this is the other sort of most common measurement in radio astronomy. And if you then integrate that over frequency, which nobody ever does, you then get flux. And so anybody who just talks about flux is probably wrong. Except when they do actually do this, which is once in a blue moon. In my career, I've seen someone integrate over frequency once. One of my office mates did it once.
Do you have an idea of why they don't integrate over frequency?
It's not usually useful. Yeah, naively is for one thing, you always have very limited frequency coverage, and so you can't integrate over the full spectrum of the source typically without making some approximations as to what that spectrum is. And so, I mean, flux is well, effectively energy flux, so it is an intrinsically interesting thing in terms of the total energy budget of your target of interest. And so it does come up in some cases, but not in the conversations that I have. So I tend to talk about flux a lot, and I am wrong. Word on units. So the standard unit of flux density in the radio is the Jansky. Thus the need for the history slide to motivate where the name Jansky comes from. 1 Jansky is 10 to the minus 26 watts per square meter per hertz. It's a fun unit. Especially when you stop to think that a watt is a joule per second, and a hertz is per second, and then you've got 1 over hertz, which is seconds. So you have a joule per second times seconds. It's a bizarre unit. So what you actually have is joules per meter squared, which does not actually help anything. But yeah, 10 to the minus 26 is the good part. This gives you a sense of the kind of energy scales we're working on here. Specific intensity tends to be in Janskys per beam, whatever a beam is, and that's an interestingly complicated topic for later today. Some people do Janskys per steradian. I've been told that infrared people like to talk about megajanskys per steradian, which confuses me because when are you ever observing an entire steradian worth of anything? That's 1 over 4 pi of the entire sky, right? So that's 1/12 of the entire sky. You never observe anything that big. And weirdly enough, specific intensity can also be reported in Kelvin, which is interestingly bizarre. And I do have slides on that because it's weird. So that is the sky. Let's talk about antennas briefly. So an antenna fundamentally is a device that converts EM radiation into electric currents, or vice versa. So there's this principle of reciprocity, where any antenna can basically work equally well forward or in reverse. If you feed it an EM wave, it converts it into a current. You feed it a current, it converts it into an EM wave. And so that tends to come up a lot in sort of antenna analysis, which could easily fill 3 other courses. And so I'm keeping the antenna section a bit short. But basically all you need is a piece of metal, ultimately. And you just a piece of metal that you've hooked into an electric circuit, generally with like some kind of amplifier because the currents are really small. And I learned this when making the slides. The plural of a radio antenna is antennas. The plural of insect antennae is antennae. I did not know that.
I've been using antennae like,
So have I.
and I've used it like in a paper that I'm writing with Brian, and he did not like circle it.
Well, you should fix
So I
it.
should
now.
tell him.
You should fix it because So if you take nothing else from this course, now you know.
That's so funny.
And so there's a lot of different kinds of antennas. This is sort of the classic kind of double or like half wave or quarter wave linear antenna. You can also encompass it in like something like a feed horn, which tends to focus radiation a little bit. So a lot of different kinds. So there's a couple of pictures here. So on the top left, this is one made by a Greek kid that I've been helping out, giving advice to. So he built his own 21 centimeter radio telescope. This is the feed horn of it. And this copper rod is the antenna here. And so that's a quarter wave antenna for a 21 centimeter receiver. And it's literally just a copper rod that has been soldered onto a standard electrical connector, like whatever the coax connectors are called. That's all it is. And there's a bit of a feed horn around it. Top right, this is a low band antenna. It is 4 wires. 4 wires held in place with elastic straps with a little amplifier at the top. So that's literally all it is a long wire.
Also a metal mesh at the bottom.
The metal mesh is just like a ground reflector, and it kind of keeps the ground noise down a little bit, and it keeps the grass out. Actually, the tarp.
No,
keeps
it
the grass
doesn't.
out. Yeah,
Yeah, it goes through. When
the
I
tarp.
saw
The
it,
tarp.
I saw one of these like 2 months ago. No, it doesn't.
4 wires. 4 wires is the antenna.
Did you go to Effelsberg to see that? Yeah, okay. Effelsberg
Yeah.
was funny because it was like the history of radio astronomy with the big telescope, and there's like new radio astronomy. It's like these little antennas sticking out of the ground.
I have pictures later on.
Okay.
So this is a low-far high-band antenna. They call these butterfly dipoles. And so they have these kind of butterfly wing shape, I guess. And I don't know why that shape is good. I'm assuming the electrical engineers have figured this out. I'm trusting them on this. But yeah. And so this is actually, so each of these, including the 4 wires from the low-band antennas, are actually 2 separate antennas as cross dipoles, so that you get sensitivity to the 2 different polarizations, the 2 different linear polarizations. And so each pair of these on the opposite side would form a single antenna, and then the perpendicular ones are a second antenna. And these are treated completely independently from an electronics perspective, so far as I'm aware. They're co-located but separate signal paths. And here's an example of a circular feed. This sort of helical antenna from some kind of satellite radar system, I think. I found it on Wikipedia. I wanted an example of a circular antenna. And so you do see some of these, like the VLA, most of the VLA's receivers are actually circular feeds as well. And so buried inside are some kind of a system like this.
These just seem whack.
Yeah.
I know, it looks so weird.
It works.
Looks like a drill or something.
So why not
Space
just
drill.
build a linear feed, which is clearly easier to build, and then convert between linear and circular?
That is a good question. I think in certain cases there are engineering advantages to having a circular feed. I don't know what those advantages are.
But you assume there must be some.
I assume there's a good reason, otherwise they wouldn't have done it.
A
You know,
dangerous proposition. But okay.
Yes, but I'm not an engineer, so I'm a practical man.
Engineer size.
Engineering.
They seem like
Full stop in that
those guys seem
corner.
like trustworthy guys.
Yeah.
Any insight?
It works. The VLA runs, right? Yeah. Any other comments? Yeah. Okay. So antenna beams is something I wanted to spend the time on because this is a pet peeve of mine. The word beam in radio astronomy. It's probably the single most overused word in all of radio astronomy, and it can easily mean a dozen different things, depending on context. And so it's important to sort of have some sense of what it can mean in different contexts. And whenever you don't know, you should definitely pester whoever is talking about it. But basically, in general, a beam is a 2D pattern of sensitivity as a function of direction, either direction on the sky, direction relative to whatever your telescope is looking, that kind of thing. Is you always have some kind of pattern of sensitivity. You're most sensitive in some direction, you're less sensitive in other directions. And so the beam is effectively the mathematical function that describes that property. And it comes up basically everywhere. You can talk about the beam of an antenna. Like an antenna is sensitive in different directions. Primary beam is usually the combined beam of all the optical elements in your system. So it's usually the antenna plus the dish is sort of the primary beam. Synthesized beam, dirty beam, clean beam are all interferometry terms. Element beam and station beam come up in phased arrays, which I'll talk about shortly. And then there's even more. And so in my first PhD paper, I got comments back from a collaborator saying, please stop using the word beam because our entire team has decided that it's too ambiguous. And we know they decided, like, I was talking about dirty and clean beams, and they just said, please use point spread function. That makes more sense in context. And so that's what I did, and I caught flack from half of my other collaborators.
Oh, no.
But you can't make everyone happy. So yeah, so specific usage tends to depend on the context and the instrument. And so it's good to make sure you're sort of, whenever someone says it, you should just ask yourself, do I know what they mean? Because it's easy to get confused. Here's sort of typically what one might look like. Here's a beam for something, pulled it off of, I think, Wikipedia or somewhere on the internet. And yeah, it's a function of direction. This is sort of a typical representation where distance from the origin is your sensitivity, and then you just do that for the different directions, in which you might conceivably look. They all have they tend to all have a common kind of shape, particularly antenna beams. And primary beams, when you include the dish, they all tend to have a main lobe in which you have primary sensitivity. This is your forward direction, wherever you're typically pointing your system. And the main lobe has some width, some half power beam width, which is defined by where the sensitivity is dropped to 50%. And so you say the full size at which you have 50% sensitivity is your either full width at half maximum or your half power beam width. And usually when people talk about a beam of so-and-so degree size, that's what they mean. People might say, oh, this thing has a 1 degree beam, this has a 30 arc minute beam. That's the size, is the half power beam width. In addition, you tend to also get side lobes typically, and so these are sort of off-axis directions to which you have partial sensitivity. You also get nulls. There are certain directions to which you could have 0 sensitivity. So you could have the brightest radio source in the sky in that direction and detect nothing at a null. Conversely, you could have a bright source in a side lobe, and you wouldn't be able to tell the difference between a bright source with the low sensitivity in the side lobe versus a fainter source in the direction of the main lobe. So this is one of the major issues in radio astronomy, is you have this sensitivity to places you're not interested in, effectively.
What does it mean by null?
So null is a point at which you have 0 sensitivity. So if you think this is basically, if you think of this as a function of direction, the null is the zeros of the function. Although in realistic systems, it tends not to go exactly to 0. And so people will also just use the word null to talk about local minima. It might minimize out at like 5 or 10% sensitivity and then come back into the side lobe.
So I have a question. So when I'm familiar with side lobes, is dealing with like interferometry, where it's caused by like different like interference of, I guess, like lobes of each telescope. So what about for like an individual telescope? Like, why do you get lobes?
Yes, no, this is purely a function of a single telescope as it is, and so
Yeah.
so yeah, in the context of interferometry, it can mean something a little bit different.
Okay.
Mostly because you have slightly different beams. So
Mhm.
this right now is in the context mainly of antenna beams, although any beam, clean beams, dirty beams, synthesized beams, all tend to have the same kind of structure to some degree. And so you see a lot of the repeats in terminology. And so an interferometric side lobe is a slightly different beast.
Okay, because I thought it was this, but then those things like interfering with each other to make something.
Yeah,
nice.
they don't actually interfere when you have a interferometer. Each individual antenna or dish in an interferometer will have a primary beam like this.
Yeah. So then why do you get side lobes and stuff for an antenna?
Well, antenna will probably not look quite like this. This is more what you get off a dish.
Okay.
And I have slides coming.
Okay, sorry.
So it'll probably make more context in the sense that the slides, particularly about why you get side lobes, are the ones I've stolen from Rick Perley.
Okay, yeah.
Because he is wise.
He
and I
is
am
wise,
not.
yes.
All right, I have a quick
So
question.
yeah. Yep. Yeah, go ahead.
Sounds like you're making some kind of distinction between antennas and dishes.
Yeah, to some degree, in the sense that an antenna by itself is, well, in strictest terms, is literally just the little wire stick that's absorbing the radio emission, and everything else, like the feed horn and the dish, is all just optical components to focus your EM wave onto that little metal antenna.
Right, so adding the antenna onto a dish will change the beam or the PSF.
Yeah. Yeah, absolutely. And I think when I get into phased arrays, that'll probably make a little more sense, actually. Because phased arrays make it much easier to actually see what's going on. So I think yeah, it'll be more clear in a little bit. Yeah, okay. And I just realized I can't actually see the clock because it's being blocked by my Zoom, but anyways, I'll assume it's okay. Oh wow, okay. Yep. So yeah, so antenna power units. So yeah, so intrinsically, an antenna converts the electric field of an electromagnetic wave into an electric current. A electric current, as it passes through any circuit, has some power. And power, weirdly enough, can be interpreted in temperature units. And this gives us the conversion from, sky, what's coming into the sky, hits the antenna, and then eventually somehow we end up with intensity in terms of temperatures in Kelvin.
Intensity or flux?
Intensity. Intensity is in Kelvin. Yes.
Okay.
Good question. So there's a really cool.
This doesn't have to do with why flux is sometimes referred to in Kelvin.
Is flux in Kelvin?
Well, isn't that what you said on your slide?
No, I.
Yeah.
Oh, okay.
So now
Okay, I was getting.
Um,
Okay, no.
What did I
So
say?
it's specific.
specific
intensity.
intensity is in Kelvin. Good. Okay. Good. I'm not insane. So yeah, there's a really cool little derivation that comes from the Essential Radio Astronomy book, which is, you can think about it this way, is, so imagine you have an antenna hooked into a circuit with some resistor in a box, black body box. Black body on the left includes radio emission. Radio emission enters the antenna, gets absorbed, generates some current. Current goes through the circuit. Current through a resistor generates power, dissipates heat. So now we are dissipating heat onto this side. We are absorbing energy on this side. We have conquered thermodynamics. We have infinite power. This is how all radio telescopes are powered. Maybe not. No, thermodynamics beats us. And so clearly we cannot violate the second law of thermodynamics. So what's going on here? And so the answer is that there is thermal fluctuations in the rest of the circuit, in the resistor. There's just random electron motions, and those in turn, in turn are electric currents which go through the antenna. Electric currents through an antenna re-radiates EM waves. And so in principle, if the two components of this system are in equilibrium, you have to have an equilibrium between power being absorbed by the antenna and power being radiated by the resistor, and vice versa. Power generated in the resistor through thermal motions has to be countered with energy being re-radiated by the antenna. And so you can talk about the thermal noise in a resistor sort of as Johnson-Nyquist noise. The amount of power per unit frequency is a function of the temperature of the system. And so you can actually turn this around. So you can say, okay, I am receiving this much power into my antenna. What is the corresponding temperature if I let the system come into equilibrium? And so this then defines the antenna temperature. The antenna temperature is the temperature associated with how much emission is being absorbed by the antenna, how much power. And so the temperature of the corresponding black body that has the same power per frequency. And so another way of saying is, my antenna is receiving some amount of power. If I took away that source and just surrounded it with a black body, what temperature black body would I need to input the same power into the antenna? So these are all sort of equivalent statements. And so this gives us the antenna temperature as a unit, effectively. And as a temperature, it's expressed in kelvins. There is a similar but subtly different variable, which is the brightness temperature. And so the brightness temperature is the temperature of a black body that produces the same intensity as a particular source. This is not talking about antennas now. Brightness temperature is talking in the context of some radio source. So you have some radio source, it has some particular specific intensity, which you can conceivably measure. And you could also imagine replacing that source with a black body, with that black body at some temperature that it's producing the same amount of radio emission within the band that you're observing it at. And so brightness temperature is our way of expressing radio intensities, brightnesses, in units of a temperature. And so this is something you talk about the actual sky emission. You can take away the antenna part. There is a process by which you can convert an antenna temperature into a brightness temperature, which I'm not going to spend time on now. Or am I? Actually, at the bottom of the slide I am. But so in general, you have some intensity. You can set that equal to your Planck equation, and then sort of invert that, say what temperature gives me the same Planck black body emission. But in the radio regime, we cheat. Everything is in the Rayleigh-Jeans limit. And you can I may do this as a homework problem, is you can sort of look at the Rayleigh-Jeans tail of the black body equation and say, at what temperature, for given frequency, at what temperature does this stop being a Rayleigh-Jeans tail? And for most radio frequencies, the answer is like 0.1 Kelvin or less. So for any astrophysical source, as long as it's warmer than 0.1 Kelvin, you are thoroughly in the Rayleigh-Jeans limit. And so if you take the blackbody equation and apply that limit, you just get a very simple relationship between intensity and temperature, which basically just involves frequency squared. So intensity goes as temperature times frequency squared, or you flip it around and temperature goes intensity over frequency squared. And so basically through that relationship, at any time, you can basically talk about intensities in Janskis per beam or Janskis per steradian or whatever, or you can talk about them in Kelvin. And single dish astronomers like to work in Kelvin for reasons that will come up eventually. And so you will randomly get people talking about the brightnesses of things in Kelvin and then have no clue how to interpret that, if you're the sort of person like me who likes to think in millijanskis.
So if a source fills the beam, TA equal TB,
Right.
what do you mean by fills the beam?
Basically completely occupies all the directions that the antenna is sensitive to.
So it's just like a really big
So-
object that's.
Yeah,
you're
well,
not seeing
you
anything
can
else.
imagine in some perfect universe an antenna that has amazing directional sensitivity and only sees a piece of the sky with no side lobes, no other sensitivity in other directions. So in that hypothetical perfect antenna, all the source has to do is fill the solid angle that you're looking at. And to some degree, in realistic terms, if you neglect side lobes to some degree, you can approximate this. And then in more realistic systems, things get messy. And I don't know enough about single dish measurements to know where all of the messiness lives and how it's solved. I am an interferometer guy. Single dish stuff is outside of my particular knowledge set. I should have warned you guys at the beginning. So there are some things that I can't necessarily answer. Yeah, dishes are actually a surprisingly simple topic because they are really just optical components. There's really minimal difference between a radio dish and a parabolic mirror in a regular optical telescope. The main difference is we are in a very different regime in terms of lambda over d for sort of diffraction effects. So if you think about like an optical telescope looking at what, half a micron-ish, if you have, so that's half a micron, so that's half of 10 to the minus 6. And so if you have a 1 meter mirror in the optical, that's, I'm trying to do math in my head here, like 2 million wavelengths across. If you try and do that at 20 centimeters, you somehow now need like a 440 or 400 kilometer dish, which is hard. So we're a very different regime, especially like if you're starting to work with small dishes of only, a few 10 times your wavelength. And so diffraction suddenly becomes a huge problem, and that's why we start seeing things like side lobes. These are really kind of diffractive processes to some degree and interference processes. I mean, the nice thing about radio dishes is because surface accuracy, in terms that you need to get a good reflection, scales as wavelength, just some fraction of wavelength, you really don't need to polish anything in the radio. And so this is also why you can build radio dishes out of mesh if you're doing low frequency stuff, is you can basically exploit the kind of Faraday cage effect and just build your dish out of wire mesh. As long as the holes in your mesh are considerably smaller than your wavelength, it's all fine.
Does that mean that if you're kind of at the limit, like a diffractive limit with your telescope, that if you're observing over a larger bandwidth, you can observe an object that has a flat spectrum, but from your telescope's perspective, you can actually have some sort of spectral
Absolutely.
feature in it, just due to it having diffractive difference across the band.
Yeah. I mean, that would be generally interpreted as changes in the primary beam as a function of frequency. And yeah, that can mess up everything if you're not careful. Yeah. So yeah, different kinds of dishes tend to follow a lot of the sort of classical telescope designs that, you see in the optical, so Cassegrain types and all the other kinds of variations I'm not going to go through. Prime focus tends to be very common in radio astronomy, less so in optical. So you just basically just need the one reflector surface, and you just stick all of your antennas and receivers up at the primary. But yeah, there are a lot of variations, and typically the higher frequency you go, the more complicated things get. For reasons I don't entirely understand. But
Well, the bottom left.
yeah, surface has to be smooth, certainly. But I mean, the reason, like, why would you put in this many reflectors? I'm sure there's a good reason. I just don't know what it is.
Yeah, that's crazy.
I think it tends, once you get into a high enough frequency regime, normal antennas tend not to work as well, and you end up with different kinds of receivers.
Yeah, stop breaking the optical effects as well. Separation.
Yeah, so you can get much more complicated. But yeah, so to bring back to what I promised Ariel in terms of discussions on nulls and side lobes and stuff, is so traditionally you can talk about the parabolic reflector in terms of ray optics, where you can just cast a bunch of rays onto the parabola, conclude that they will reflect to the focus because of law of reflection, and you can actually derive that every ray has the same path length. If you come in with a plane wave, every ray then has an equal path length, and so it will all arrive at your focus in phase. And so all of the incoming rays arrive in phase, and they co-add to give a much stronger signal, which is the entire point of the dish. This is effectively an amplification device, giving, focusing all the energy into a much smaller area. And we've lost Vincent, okay. And so this is all well and good in the sort of ray optics limit, but because we're dealing with such long wavelengths, that tends not to be a good description of how things work. And it also doesn't work when you want to go off axis beyond looking straight up or straight out of your dish. And so typically you need to go, this is again a slide I've stolen from Rick Perley, but typically you need to start thinking about wave optics. And I hate the math, but I'm quite fond of the Huygens-Fresnel principle, which is the idea that you can think of an EM wave as sort of every point is re-radiating, spherically, and then you sort of integrate over your wavefront to see how all of that re-radiation behaves coherently in terms of phase addition. The math is really gross. I don't want to spend time on it. It's not that relevant. But the net effect is, if you think of it that way, you can't justify a off-axis wave coming in and hitting the focus in terms of ray optics because you're violating the law of reflection. But in sort of wave optics, you're allowed to do that. And the end result is that things start to arrive at your focus out of phase. And yeah, Rick kind of goes into more detail about this. He has some follow-up slides that I'm skipping. But the net result is you can imagine, what if the signal at one edge of the dish is out of phase with exactly out of phase with a signal coming here. Two signals arrive out of phase, complete cancellation. And then you move in the dish a little bit. This one cancels this one cancels that one, all the way. Every signal coming into the dish has a component out of phase that matches it. And so if every component has an out of phase partner, you get complete cancellation, you get a null. You have zero sensitivity in that particular direction. And so you can sort of derive that direction is proportional to lambda over your diameter. And so this is sort of comes back to why you get nulls, essentially. And this also, if you go through this kind of explains why your beam width scales as lambda over d. So this is your classic resolution criterion lambda over d kind of equation. And with some numerical prefactor, depending on, are you defining half power beam width? Are you defining the first null? You get numerical prefactors that aren't interesting. But resolution basically always scales as lambda over d with some numerical factor. And so that's a surprisingly powerful result, derived for dishes, but it's actually a very general result.
So just to make sure I have this clear, the side lobes are basically like when the actual waves that you're measuring start to interfere with each other. And it's basically
Well, not even just side lobes. I mean, as soon as you move off axis at
it's
all,
still interfering.
you're getting partial
Yeah.
partial destructive interference.
Yeah, because it's not perfect.
Yeah, the null is perfect destructive interference, and then you start having more imperfect. So you have some cancellation, and then some leftover signal that's not completely.
So if you just
destroyed.
have one antenna with no dish, do you still get that?
Yes. Yeah, an antenna itself has some sensitivity patterns.
Okay. But it's not like
The sensitivity patterns of antennas tend to be complicated depending
Yeah.
on the shape of the antenna.
Okay,
Does it
yeah.
have a feed horn? Does it not?
Yeah. Okay.
What is it like? And so you can actually design different shapes of antennas to have different sensitivity patterns. So this is like cell phone antennas, for example, or like cell phone towers want to cover
Right.
every direction wherever a cell phone might be. So they design their antennas to have the broadest possible beams, essentially. Stuff like that.
The sensitivity pattern is kind of important too. Like it kind of tells you where you're pointing. Like if you didn't have a sensitivity, you wouldn't have the
You'd be
any
equally
nulls,
sensitive in all
but you would-
directions. Yeah.
Exactly.
And so to some degree, this is an important tool for filtering out directions you don't want, which will come up shortly, actually, and is actually very useful for interferometry in some ways. Although there are cases where maybe you do want to detect everything. And so then you suddenly have a very different set of criteria for what makes a good beam if you want to be sensitive to the whole sky at once, maybe for transient studies. It's now phased arrays, which I'm very fond of because I worked on a phased array for my PhD. Again, a Rick Perley slide. He expressed this in terms of interferometry, but I think this is really a phased array topic, which is the whole point of having like a parabolic reflector is you get all of the rays hitting the focus at the same time. So what if you just didn't have a big reflector? What if you had a whole bunch of just little antennas and you just added the signals together such that all the signals were electronically combined at the same time? You get the same result. If you have the same collecting area, all of the same photons, talking about radio in terms of photons is really weird because we're not in a photon regime. We always have quadrillions of photons at our disposal. But you can think about it, it's like all of the same photons going into your antennas, they're all getting absorbed, they're all being converted into electric signals. Why do you actually need a dish? And this is the principle of the phased array, which is the idea of having multiple antennas and adding these signals in phase. And this is, stole this off Wikipedia. This is the same thing in reverse. This is a phased array transmitter. And it's the same thing. You have some source of waves, just like a signal generator. You introduce time delays between the different antennas, or time or phase delays, same thing. And so you can I actually pause this? Maybe not. Okay, maybe not. But no, there it goes. So you can see like the waves are being transmitted at different times. And so the net result when they interfere with each other is you start to get the net effect of transmitting power in one direction, or transmitting a signal in one direction. So you can effectively build a plane wave or something like it out of many sort of transmitters. And so, and by changing the time delays between the individual components, you change the direction that you're either transmitting in or the direction you're sensitive to if you're receiving. And so this is a great animation. All you're doing is changing the relative phases of the different components in a coherent way, and suddenly, boom, completely different directional sensitivity, different beam. And so this is a surprisingly old technology. This is a World War II radar station, and it's very hard to see, but there are a lot of little antennas on a grid here. And so the technique is not new. It's just the ability to have digital electronics and very cheap electronics that makes this a very attractive thing in recent years. So this is a typical LOFAR station, LOFAR being a phased array system. one that's close to my heart. And so each of these LOFAR stations, so if we focus on the low band on the left, there are 96 pairs of antennas, right? Each of these are these little wire, so you have the 4-wire 2 antenna. So there's 96 of them, and by adding them up with different time delays, you can control the time delay, and it gives you sensitivity then 2 different directions on the sky. And the same thing here. So each of these little black squares is a 4x4 grid of those little butterfly dipoles. So you have 16 butterfly dipoles in each little black square, and then 64 of those squares. And so you have some hundreds of antennas in there.
So like you don't have to actually point in the direction
So
of the
you
sky,
don't-
you just gotta like,
No moving parts.
yeah.
All done with electronic signal delays. And so the net effect is you choose the signal delay, you control it, you can change it. And that changes how signals will add together. Are they going to be in phase or out of phase? That will depend on the direction and on how you've chosen the time delay. And so you can simulate having a dish pointed in any direction without the moving parts. And so coming back to beams, because this is, I think, a good demonstration of how messy it gets. So you can talk about beams of the different parts. And so each antenna has some directional sensitivity. It's just a couple of wires, but it still has different sensitivity depending on what direction it's coming from. So this is, in LOFAR terms, they call this the element beam. Each element is a single antenna. And it tends to be more sensitive to emission at the top than from the horizon. And then you take a bunch of those antennas and you phase them together. So this would be in the case of the high band, each of those boxes, each of those black boxes is 16. You phase them together into a subarray where you again have sensitivity in some direction based on those. And then you can combine all of the boxes together. And because you're further apart, you're simulating a larger diameter dish. And so the size of your beam, again, follows this sort of lambda over d dependence. And the really cool thing, although I'll talk about digitization a bit later, is if you digitize your signal, before you do the addition in the phased array, you can just copy digital signals. And so you can make 100 copies of it, change the time delays, and then add them together. And suddenly you're looking at 100 different directions at once. And so, yeah, LOFAR can do that. I mean, there are some restrictions. Like if you already have the subarray phased up, you have some sensitivity pattern from the phased array. You can't change that by magically being sensitive to some random other direction. So there are these kinds of restrictions. But you can control, the principle of phased array is you control what direction you're sensitive to by adjusting time delays, and doing this digitally gives you much stronger control over copying signals, changing the times, doing what you want with the signal.
What if it's a mixed telescope where you have some sort of dish, but then you also have the ability to phase as well?
Mm-hmm. Yeah.
You can't really, I suppose, you can't really overcome the
beam of the dish.
The beam of the dish.
No. So every time you start phasing things together, what you're basically doing in terms of beam patterns is some kind of product. I have to think about the mathematical formalism here, but it's sort of a product. Is if you take this an element pattern and you multiply it by itself 16 times, right, it becomes more and more focused. And so that's essentially what it is. So yeah, I did forget to say it. So each beam is also intrinsically a complex quantity. Oh, this is the next slide. Yeah. I planned ahead. Beams as Jones matrices. And so you can think of each beams as affecting, in theory, it can affect the polarization state of signal that's coming in. And so you can have an incoming signal with some polarization state, which you can express as a Jones matrix or Jones vector. And then as it passes through the dish and the antenna, it gets modified in some way by the beam. You're either more or less sensitive, you can more or less amplification from the dish as a function of direction. And so you can express that as your beam pattern, as a function of position, you have different sensitivity. It'll also alter the phase of the signal potentially. And so each beam, I've been showing them just as these functions that, you know, seem like they have some amplitude. There is also a phase factor in all of these beams. So a beam is an intrinsically complex thing. It modifies the amplitude and it can modify the phase of the signal relative to whatever the incoming signal is. And so each beam is a complex thing, and it can alter the polarization. So you can have a beam. This is one from the VLA done by a friend of mine. And the VLA, as I said, has left and right circular feeds. And so you can express these as the right circular and left circular feed. You know, the dish itself modifies left circular polarized emission in some way and right circular. And it also converts some left circular into right circular because of imperfections in the dish. And so you can express that as a beam. And so suddenly you have this 2x2 complex matrix, which is also a function of position. And so it all gets messy. But one of the really cool things that you can actually see in this, you can see that this beam is not completely circularly symmetric. You know, if you had just a purely circular dish, you expect circular symmetry in the beam. There's kind of a vague squarish pattern, particularly at the edges. And the reason for this is the 4 support legs on the VLA.
Oh.
You have this 4-sided symmetry in the support legs. You get a 4-sided symmetry in the beam, you know, being modified by that. So we're over an hour in, aren't we?
Mm-hmm.
Does anyone want to take like a 5-minute break or something, or should I keep going? Okay, because I am behind, so I do want. If everyone's okay with me just keeping ranting. So yeah. On the topic of phased arrays, actually, so getting into the details a little bit, I want to talk about geometric delay. This is something that affects phased arrays, and it's also important for interferometers, so I'm introducing it now, which is geometric delay is essentially just the difference in arrival time for if you just consider 2 elements in your phased array. You know, a plane wave comes in from some direction, hits one antenna, sometime later it hits a second antenna. And so the geometric delay, tau g, is that time delay, and you can express it in terms of there's like a baseline vector going from telescope 1 to telescope 2, and the look direction. So you get the b dot s, and I'll leave it to you if you want to sit down and do the geometry to convince yourself that that is the correct equation for it. But the net result is that the signal coming out of antenna 1 then is the same. You end up with the same signal, but delayed by this geometric delay factor.
So you have 2 types of delays. You have geometric and the ones you introduced. So you know when you showed the transmitting the gig.
Yeah. So those are kind of distinct. So yeah, geometric delay is a pure, it's a pure geometric factor. It's purely the orientation of the antennas relative to your signal. So yeah, the time delays that you choose to set they are actually a different thing.
Right.
And they are related because ultimately the point of choosing a delay in a phased array or an interferometer is to either manually create the correct geometric delay, so to sort of cancel it out or introduce it to get the right phase behavior between signals.
You need to know this accurately.
Yes.
To then
Yeah. This is a really interesting thing. And so there's a couple of important reasons for this. First is for phased arrays. Is you need, for a phased array, you pick your look direction, and you say what geometric delay is going to happen given the configuration of antennas and that direction. And so, what geometric delay do I need to introduce? What delay do I have to introduce in my circuits to allow all the signals to arrive in phase at the adder, essentially? So yeah, for a phased array, that's essentially how that goes. Is you choose a direction and calculate the delays that you need.
So wait, so you pick a direction, and then for each antenna in the phased array, you just kind of offset this geometric delay, kind of, so that everything's arriving in phase.
So for every antenna, there will be a offset.
Yeah, some sort of small geometric delay.
Yeah, so it could be a few nanoseconds kind of thing. And in order to make sure that when you've then taken this, you take the electric signals, you add them together, you want to add them in phase for that particular direction. So you need to know what time delays to introduce.
Okay, so you do that, and then you can like add on extra
You can
delay, phase, whatever, so you can then also look in different
yeah. So
directions.
you pick a different look direction.
Yeah.
You now have different geometric delays for every antenna.
Oh, okay.
And so, yeah, for a phased array, you choose first, and then that tells you what the geometric delays, what the delays you have to put into the system need to be to match the geometric delays. Because when you properly match the signal delay to the geometric delay, then all the signals will be in phase when you have them. That's the goal.
So this is how you determine the.
yeah. So this is just a mathematical equation.
Do you have to do it at the time of observation, or can it be like the post-processing?
Yeah, that is a good question. So,
Isn't it basically just interferometry?
Because if you know it value, you can do it.
yeah,
after.
so it kind of comes down to signal processing. So you can do it in post if you record every individual signal from every antenna. So if you recorded a signal from every antenna, the full time series, you can then modify that time series offline and then co-add digitally. So that's entirely possible. It does require you to then record everything. And so typically if you're trying to do things live, you're then limited by processing power. So LoFar is intrinsically limited by processing power. You can, I think it's something like 488 simultaneous beams basically, but you can either have 488 beams at different frequency in the same direction, or you can have the same frequency in 488 directions, or because it's basically every channel gets processed in parallel with LoFar, and so you throw away half your frequency information in order to get double the direction information. It's kind of, you have these kind of trade-offs. You can choose observation. There is an additional kind of important thing. So I did introduce the quasi-monochromatic approximation for a reason. It has not come up until now, but so we have again this approximation that the wave parameters are only consistent or constant within some coherence time. And so imagine if you didn't correct for geometric delay, you have signals coming in. Imagine if you just did some kind of like a phase correction. You said, oh, I'm only going to make it so that the signals are in phase, but they're actually like 6 pi phase difference between them, right? Some multiple of 2 pi. That doesn't work because after a coherence time, the phase isn't going to be consistent anymore. And so geometric delay is actually really critical because if you want both antennas to have signals with the same amplitude and phase coming in, it has to be the same wave. You can't have a time-shifted version of the wave because the time-shifted version, if it's outside of the coherence time, will not be the same wave anymore, essentially. And so this becomes really critical even for interferometers. Yeah.
So I think I'm just a bit confused about a quasi-monochromatic wave. Like, why is there a coherence time? Like, I just don't understand.
Yeah, it's a bit bizarre, and I haven't found any good diagrams for it.
Like, because I get, like, monochromatic wave, you just got, like, the same thing coming in, but, like, I don't get
it. I mean, think about 2 waves at slightly different frequencies. You get beat frequencies between the 2, right?
Yeah.
And so sometimes you get a high amplitude, and then sometimes you get low. And so that's essentially what's happening with the monochromatic limit. Quasi-monochromatic limit is you can think of it as sort of closely spaced frequencies, so they're beating against each other.
Oh, is this because you're observing over a bandwidth?
Yeah, you have some channel width essentially, and so this is so this is sort of how we control it. Is we will always observe some channel, and within that channel you have this range of frequencies, and they're essentially constantly beating against each other, so that within some short period, you still get the dominant sinusoidal, and if you wait long enough, you get the beating envelope where it tends to, the amplitude tends to shift and the phase tends to shift. So that's ultimately the origin of it.
That makes so much sense.
And so that's why you can't combine 2 drastically different signals. And so yeah, I've included this because I think it's really cool. I mean, this is very important for phase arrays and for interferometers. This is usually taken care of at like the system engineering level, but I just found this a really neat bit of system engineering about how you the older fashioned systems tend to build this. Newer systems do this digitally, but you have to basically set a certain amount of electric delay. And so how they would do that is you have some input voltage, and then depending on the amount of delay you needed, you would basically set a bunch of switches. If you needed, you'd have some minimal delay, which might be, say, a nanosecond. And if you knew you needed 6 nanoseconds of delay, you would set the switches to go through the 4 loop and through the 2 nanosecond loop and then out. And so you could just do this with these binary switches. If you need 24, send it through the 16 and the 8. And so all you need to do to change your geometric delay is just change the switches, which are all just relays, so it's electronic. And so you have some minimal sort of quantization scale, which you have to set, and then you set that depending on something. You can ask yourself, how accurately do I need these to be in phase? How accurately do I need to control the time? And so that sets through sort of minimum scale. And so this tends to be how systems would sort of account for that. And so I actually got to see some of the delay lines at DRAO a few years ago for the radio telescope, for the interferometer. Right, so we've gotten from 2, the sky plus 2. But the rest of these will kind of go a lot faster because they're less interesting from a scientific perspective. So just sort of for the sake of seeing them.
Sorry, before we continue,
so
can I ask?
Sorry, the volume is really high, so every time you speak up, I jump. Say it again?
I wondered why I was laughing. I'm sorry.
No, it's me. I'm really jumpy, so
Oh.
go ahead.
I was just hoping you could explain the distinction between an interferometer and a phased array. I don't really understand what the difference is.
Oof.
I thought they were the same thing, but it sounds like they're not.
Yeah.
Is it just a question of like live versus after the fact?
No, because interferometers can work live. So the main distinction, so there are 2 levels of answer. So I got asked this by a member of the public once when I was actually at the VLA. And the answer I gave them is that a phased array is all about the addition of signals. Is you're taking the signals from the different antennas, you basically just co-adding the signals, and then they basically interfere constructively or destructively depending on phase. With an interferometer, you actually end up multiplying the signals together, and that gives you a very different output. And what that output is like the first half hour of next week's lecture. And so the slightly more technical answer is that with a phased array, you pick a direction and you phase up such that you are maximally sensitive in that direction, such that every signal in that direction adds in phase, and signals from other directions are sort of partially interfering. So that's the principle of the phased array. Interferometer, because you're doing a slightly different mathematical operation, what you get out is you're not necessarily picking a direction with an interferometer, and so what you actually get out is something that is you get a product out that is partially sensitive to the direction it's coming from. And so rather than setting a direction and getting a power measurement out, is the interferometer is telling you something about the direction it's coming from. And so that's part of what makes an interferometer more powerful, is rather than having to choose, measure, and then choose again, measure again, choose again, measure again, the interferometer sort of gives you all the information right away with some caveats. That's the short answer.
I think there are telescopes like this, because I think like ASCAP might relate this, where you have phased arrays plus interferometers.
Yes.
So, but then do you have to, that probably just be so complicated.
It is a mess. So LOFAR does that, ASCAP does
Yeah.
that. So with LOFAR, each station is a phased array.
Oh,
And
right,
so the output is each station gets phased together, and the output is 1 voltage signal, essentially. Well, 2, because of the orthogonal polarization.
Okay.
But
So
so you
as
get 2 voltage signals out. Sorry?
So as examples, LOFAR and ASCAP are phased array, but ALMA, for example, is an interferometer?
Yes. ALMA and VLA are pure interferometers.
But ASCAP is a phased array plus interferometer.
Yes. Yeah. So is LOFAR.
And LOFAR, yeah.
So LOFAR is at the station level, and ASCAP is on the dish. On the dish, they have an array of antennas at the focus, and then it phases up the block in the focus there to give basically slightly different sensitivity. I want to say to different directions on the dish, and that's not true. It's a bit of a phased arrays attached to a dish are a really mess to visualize. But the net effect is you create beams on different directions in the sky with the phased array. And yeah, And
Is
then
it-
and then with each
Sorry, there's a bit of a delay, so I don't mean to cut you off. It's just a
yeah,
delay.
it's fine. It's fine. Go ahead.
I was just going to ask, is it coincidental that the lower frequency telescopes tend to be phased arrays, whereas the higher frequencies are interferometers?
It is not coincidental.
Okay, so there is a reason.
And the answer is there is a reason. The main reason is lambda over d. The longer lambda is, the longer your diameter has to be to get the same resolution. And for the dish effectively. And so at some point building multi-kilometer dishes is not really economical. And so, I mean, to some degree, just building dishes at all becomes less economical because electronics are really cheap. Low frequency electronics are really, really cheap. And so building 100,000 low frequency antennas is actually not that difficult a thing to do. Versus high frequency instruments are more complex, they're more expensive. And so you don't want to be building as many of them. And so you're better off building just a mechanical structure like a dish to do your amplification is sort of the easy answer to that. I feel like there was another question I was halfway through answering.
So like, do you finally do the phase delay with single dish or density?
Well, see, I mean, you can do the stuff with a single dish, but there's not a lot of value to it. Is this all? I mean, you need multiple antennas for any sort of phased array, because the whole point is that you want to combine the signals. And so you'll need to have multiple antennas to do this. You can have multiple antennas mounted to a single dish. This is the phased array feed principle, which I don't have any pictures of, and I was actually planning to get into. But yeah, you can effectively mount a phased array on a dish and get some interesting effects out. But that's kind of out of scope. Anything else? Okay. Amplifiers.
The
So.
time is almost 4:40. Just so
Oh
you
my
know.
goodness.
Just,
Okay, I'm gonna go really fast. So amplifiers are basically just signal, they boost the signal strength. They're necessary because radio signals are super weak. They also amplify noise that comes into the amplifier. So there's a lot of sort of engineering considerations about where do you put an amplifier in your circuit and how much noise is it adding, and where do you want to put the expensive high quality amplifier versus the cheap amplifier, stuff like that. Important things, I think, are that an amplifier needs to be an intrinsically linear process. It needs to basically, you need to trust that it's going to multiply the input voltage by a fixed amount, because that's an important part of calibration. Is we always trust that whatever voltage we measure, there is a simple conversion factor from measured voltage to sky intensity. And if you break that, then calibration becomes really hard. And the reason I mention that is that's actually become an issue right now for like the VLA, because they've had issues where if the VLA points at certain declinations where there's a lot of satellites, suddenly picking up a lot of RFI, and you can filter that out, but it's still going through your first stage amplifiers, and it's really bright. So suddenly you're putting a huge voltage through your first stage amplifiers, you're pushing it into a nonlinear regime, and so even if you correct for it later on, it's still modifying all the lower intensity signals that are going through at the same time. And so this was a huge calibration problem for them. They were basically unable to calibrate VLA data in certain chunks of the sky where all these satellites were. And they basically solved it by stepping down their first stage amplifiers to a lower level of amplification so that they weren't going nonlinear. And it cost them about 30% of their sensitivity. So it was rough. But basically, calibration is more important than sensitivity. No point having amazing data if you don't know how bright it is. You can't calibrate it. So that's the thing. And also, yeah, frequency dependence is the other thing. Is amplifiers have a different gain, tend to have a different gain as a function of the frequency. So if you're putting through a lot of different frequencies through the same amplifier, and then you channelize them and you measure them, the different frequencies separately, they have to be calibrated for that effect, for that frequency dependence in the electronics. And so that basically becomes the bandpass calibration. The bandpass is the frequency dependent response of your instrument. And so that's a thing you have to calibrate for. Bandpass filters are the opposite side of things, is sometimes you want to damp out an unwanted signal. Things like known RFI sources are a big deal, as well as removing the frequencies that you're not observing so that your electronics are only dealing with the signal that's relevant to you at a given time. And so there's a lot of aspects to that, which also change your frequency response, but aren't typically that interesting otherwise astronomically. Heterodyning is a little bit funky. It used to be a really big deal, especially for the VLA, but they've kind of made everything simple so far as observers are. And this is a really interesting sort of process, I think, physically, because traditionally, as I was saying a couple of minutes ago, high frequency electronics are really hard to build. I mean, this is why low frequency computers were sort of the first ones. Like, the Commodore 64 was at 1 megahertz. My first computer had a 20 megahertz processor, and even now we basically capped out at a couple gigahertz for standard like CPUs, because that's basically what we can build cheaply. And so when we go then to digitize a signal, we need electronics that run fast enough, and the Shannon-Nyquist sampling theorem says you need to sample a signal twice as fast as the highest frequency. And so suddenly, if you're trying to measure a signal at 2 gigahertz, you need electronics running at 4 gigahertz. If you're trying to measure a signal at 30 gigahertz, you need a 60 gigahertz sampler. How on earth do you do that? And so you cheat. There is a method of down converting a signal in frequency such that you completely preserve the information of the signal in terms of its amplitude and its phase, which is very critical for phased arrays and for interferometers. So you completely preserve the characteristics of the signal, you've just converted it from a high frequency to a lower frequency. And so this used to be a really, really big deal. And so, again, a slide that I've stolen now, this one from Todd Hunter at NRAO. And the sort of method of doing this is use something called a mixer. I don't know how they work other than black magic, but it's 2 signals go in, 1 leaves. One is a local oscillator signal. So you create, using some kind of signal generator, you create a signal at a known frequency, a reference frequency. And then you input your, radio frequency, whatever your measured frequency is, your input signal comes in. And the net effect mathematically is it just multiplies the 2 signals together. And so if you have 2 sine waves, we're back to pure monochromatic signals here. 2 sine waves come in, the output is 2 sine waves at a different frequency and the sum of the 2 frequencies. And so as long as your local oscillator is close to your actual frequency, the difference becomes a small number, and the sum goes off to some ridiculously high frequency and you ignore it. And so you could have a signal at 30 gigahertz and you feed an oscillator at 30.5 gigahertz, and the net result is you get this output at half a gigahertz with half the amplitude, but that's fine. You can correct for that in post. And so the net result is you can basically take any signal at an arbitrary frequency and down convert it to somewhere you can work with it. And there are a lot of weird complicating factors, like the fact that you have a lower sideband and upper sideband, depending on, basically you always end up, because this is symmetric, is you can have F1 higher than F2 or F2 higher than, F1 lower than F2. So there's a lot of fussiness about filtering and making sure you only get the signals you want, and I don't want to spend time on that because it's not interesting. This course is very much driven by what I find interesting, but it's also not relevant to people doing astronomy. It used to be when you did a VLA observation, you'd have to set all kinds of stuff like what do you want the local oscillator frequency to be, and what kind of bandwidths and stuff, and there was a lot of restrictions. Like my first VLA observation was like, okay, you had to observe, certain frequencies and certain bandwidths, and they had to be so far apart, and you couldn't move them arbitrarily. It was just a mess. And then they upgraded the VLA, and everything's easy now. So that's digitization. So at some point, we want to go from having just analog voltages and currents into digital signals, because those are easy to store, easy to manipulate. And so there's this analog to digital converter step. I don't know much about them. I think the only sort of interesting aspect that I want to mention is bit depth, which is kind of cool, which is how many bits every measurement is. And so intrinsically, right, number comes in, you measure the voltage, you record it as a number, how many bits are you using to record that number? And it turns out you don't actually need that many bits, because and you're almost immediately going to be doing signal processing, which involves averaging and other operations, and down conversions of various kinds. And so you can start off with very few bits and still end up with accurate information at the end, which is really good if you're trying to control how much data you're producing. And so like the VLA quite standardly operates in a 3-bit mode. The voltages come in and it's only 3 bits. You have eight levels of digitization in the voltage. And that's all it takes to run fine. And there are systems that have run with 2 bits of digitization, or 1 bit I think is even possible. It's like you can just record the voltage high or low. And if you signal process the hell out of it, you can still get the right result. And it's basically black magic. But yeah, but there's a lot of advantages. And so you can do this at different stages in the process. You do have to go through all of the stages I've talked about already. But there are, well, I mean, some of the stuff like the IF, the heterodyning and down conversion, you can skip if you're already at low frequencies and stuff. You can technically do digitization before beamforming or as part of the beamforming, the phased array bit, sort of at different stages. You can do phased array beamforming after digitization, like LOFAR does in some cases. And some of the advantages are that digital information is less vulnerable to noise. The sooner you get it out of the analog components, the less analog noise you're adding to the signal. Duplication, I mentioned a couple times, is you can just copy digital information if you want to process it with different time delays, different phase delays. It's really easy. That's something that's actually really hard to do with an analog signal. You split an analog signal, you have 2 signals of half the strength. That's a bit of a weakness compared to digital signals. So there's, so that tends to come up at some point. Channelization. And so raw voltage time series are not that common in radio astronomy. There are a few applications where you actually want to specifically record the voltage as a function of however many nanoseconds. But for the most part, we're more interested in the distribution of signal over frequency, particularly because the amplifiers and the bandwidth filters have modified that, and it's easier to work with in frequency space, as well as a lot of the astrophysical information lives in frequency space. And so nearly always there is some kind of a Fourier transform from a time series into a Fourier signal. And because that's, as far as I'm aware, always digital, it's you end up with a quantized number of channels. And so this is also sort of the channelization step. Convert your time series information into a signal of n channels, where n is something that you generally want to control depending on some of the properties of your observation. Yeah.
So I've heard of the term like up channelization. I've never really understood what it meant, but is it just then like, I guess, putting in different values for your Fourier transforms? Like, do you have a different channelization for your?
So in some cases, it's possible to reprocess and change the channelization.
Okay.
And Thomas is nodding, and I think Ryan knows a fair bit about this. Come on, you've been doing this. Haven't you been doing it?
It depends on what is the baseline data. Like China, we can sort of, but it's not true.
There are instances where you can do this, and I don't know that much about it.
Okay, because I came across this when I was doing like scintillometry like way back, and they're like, let's just channelize the data, and I'm just like, okay, cool, I don't know what that means.
Yeah, in principle, if you record everything, you can go from the Fourier transform, you can inverse Fourier transform back into the time series.
Okay, yeah,
And
because
then
they're using
change
like
how you're
arrow
computing.
data, so
Yeah.
I guess they just have everything.
That works if you have to have literally everything.
Yeah.
And because typically the first thing you do after you do this is you start averaging.
Okay.
In most data, in most systems, you start averaging your Fourier transform, and then that does terrible things. For one thing, like a Fourier transform is an intrinsically complex quantity, and so you input a real time series, and you're now outputting complex numbers, and so your signal amount is doubled immediately. And so you can ask yourself things like, do you need that whole signal? Do you care about the change in, phase of channel between one microsecond and the next? So sometimes information gets thrown away depending on your system design. And that can affect then what you can do with it in post. So there's that. And so you get a bunch of FFTs out, or a bunch of Fourier bunch of spectra out of Fourier transform, and then there's a lot of different ways of processing them. And so the easiest one is, if you don't care anything about time evolution, is you just start averaging spectra. You produce a spectra every n/2 delta nu seconds, depending on your bandwidth. And so you can just, for some telescopes, that can actually be a really small number. You might be producing thousands of spectra per second, and you don't think your system's going to evolve on a millisecond timescale. You just start averaging. And this does some messy things, because if you just sort of naively average signals, now let's start going back to the quasi-monochromatic limit. So the Fourier transform is literally giving us that amplitude and phase factor of our quasi-monochromatic wave. And so those numbers are going to have some amount of randomization per coherence time. So particularly the phase, as the phase gets randomized, your complex number, if you think about the complex plane, your number for the amplitude and phase is going to start wandering through the complex plane. If you just vector average that as a complex number, it might average to 0 in the plane. And so what's typically done then is you average in power. So you take the amplitude of your Fourier transform and you square the modulus. Square the modulus? Yeah, you basically convert it to amplitude squared. And you throw away the phase information, and then you average the amplitudes, and then that gives you the power of the signal.
Do you lose signal to noise doing that?
In some context, you're losing information because you throw away the phase in doing that. And so once you've done that, you're no longer able to do phase-sensitive things like phased arrays or interferometry. And so there is a messy diagram here about different computational techniques. So, what you're ultimately getting out of the telescope before Fourier transforming is some time series of voltage. And from there, there's different sort of pathways of signal processing. And so the one I described was the Fourier transform to get a Fourier spectrum as a function of time. And then you can just average that over time, and you get this sort of time averaged power spectrum, but you've lost phase information. The other approach is you can do an autocorrelation, and I don't know how that works. And then there's like all these autocorrelation theorems, which says you can basically get a power spectrum, and it's all very cool, but I don't know how it works. Yeah.
All over time.
Yeah, that's over time. And then the net result, if you do all of this, is you just get a power spectrum that's been averaged over your observation. So this is sort of the traditional single dish output, is you get the power as a function of frequency integrated over some observation duration.
The cool thing about this is, like, the past, this used to be done like analog.
Yeah.
Digitally, so having a small delay to correlate.
Yeah.
That's great.
Yeah, there's a lot of amazing things in the early telescope. And so, yeah, so if you go all the way to the power spectrum, you start losing phase information, and so then it's kind of irrecoverable in terms of doing certain things like interferometry. And so if you're doing interferometry, you would stop, here, and then start doing the interferometer operations, which will come up next week. And I'm not talking about polarization much right now, but I do want to point out that all of this is for a particular antenna. Any given antenna is only sensitive to one polarization, either X or Y or left or right circular. So you do all of this, and you get your sensitivity to one polarization out. If you want to do this, for the other polarization, you need a second antenna, not a second dish, thankfully, but a second antenna and a second electronic signal chain to get all the way to here. And then there's ways of getting, you can actually recover the full polarization state of the wave by doing different types of correlations or different kinds of products of Fourier transforms. And that's a whole paper that I'm not going to inflict on you guys. But yeah, Tim Robichaud at the RIO wrote a really good paper about how to do that part. So if you want, I can send you that paper, but otherwise. So I think I'm down to my last few slides, actually. So the radiometer equation it's an equation that talks about power and sort of the measurements of power out of this kind of a system. And so the Condon and Ransom book have a sort of a physically motivated derivation, which is a bit long and I found a little difficult to follow. So I then went ahead and rederived it in mathematical terms, which worked for me, but I think will probably not be very comfortable for everyone else because I think about math in funny ways. But I'm just going to very quickly go over it, and then you can read the notes and decide how confusing they are. But yeah, so consider this kind of a system, but you're only interested in one channel. So you basically end up integrating the power within some bandwidth of that channel. So everything like we've discussed. And so all of the signal in the system, which includes all the thermal noise, the noise in the amplifiers, the actual sky signal that you're interested in, which is like the antenna temperature signal, you can sort of vaguely model them as like a Gaussian random process with zero mean, because everything's oscillatory, it's all waves. Zero mean, some sigma, Gaussian sigma. Basically wave your hands and chant central limit theorem a couple times. And then the process that I just described converts everything into a power, which is positive definite, and so you end up with something kind of like a chi-squared distribution with some mean and some variance, which are described in terms of the sigma voltage squared, which has units of power. So yeah, you do that, which has units of power. You can convert it then into system temperature or antenna temperature kind of equivalent. I've skipped a lot of steps in the derivation because it's really not that interesting. But what you end up with is something called the system temperature, which depends on basically the voltage fluctuations in the system and your bandwidth. And it's the temperature equivalent of the power being produced in your system. And this is typically noise dominated. Because just because radio signals are intrinsically weak. And so system temperature tends to be a measure of how much noise is present in a telescope system, and you want to kind of minimize that because noise is bad, basically. And so it is slightly distinct from antenna temperature, which is this, the power coming into the antenna. This is now the power coming out of the whole system, which is noise dominated. So yeah, and then there's a corresponding uncertainty in your power measurement, because I mean ultimately we're not measuring fluctuations in voltage. That's not something that we're interested in sort of at the human scale. Is we're interested in the power that's coming out, and then our ability to measure that power accurately. And so when you go through all the statistics of it, you get some uncertainty in your system temperature, which is proportional to system temperature, for a single measurement. And so you can then say, okay, for a single measurement, you have a really high, like this is square root of 2, so it's 1.4. So if you just did a single measurement, you turn the telescope on for some microsecond, you do power measurement, single power measurement, your uncertainty is 1.4 times the actual power when you go through the statistics of it. That's rubbish. 140% error. So you average together n independent measurements. But what constitutes an independent measurement in the quasi-monochromatic limit is if you make multiple measurements in the same coherence time, it's not really independent. And
so is it over different coherence times?
So your time is your coherence time, your 1 over bandwidth. And so your number of independent measurements then is the coherence time, and then why does the bandwidth pop in again? Oh no, it just popped. Okay, so you have a total observation length tau. Each independent measurement is this delta t from that, And so when you rearrange it, the number of independent measurements is the total observing time times the bandwidth, which you can kind of think about how this is proportional to the number of photons coming in. The wider your bandwidth, the more photons at different frequencies you're accepting. The longer you observe for, more photons arrive, so the more signal you have. And so what you end up with, and I have a problem of a factor of √2 when I derived this compared to the textbook, but the important result is your uncertainty in power goes as the power divided by the square root of this factor. And so the longer you observe for and the more bandwidth you have, the lower your noise is, and so the better your signal noise is. And so the net result is you basically just recover the sort of the classic signal to noise result, which is, observing more is good. So that's a lot of work for a very boring result. But the nice thing is that this factor, so I mentioned, error in a single measurement is 140%. But this product of observing time times bandwidth tends to be really, really large, 10 to the 8 or so. And so suddenly your error in power can drop to 1 part in 10 to the 4 very easily. And so that's how we're able to isolate signals that are weaker than the noise. And so I found that really amazing. I didn't appreciate that before I put this together, which is that you can have a signal, a radio signal that goes through all of your amplifiers, all of your signal processing, and the signal to noise is still way less than 1. You put it through all of your electronics, and you still have no idea that there's actually a signal there until you average by a factor of 10 to the 8. And now you suddenly have a statistically significant detection. So that, I think, should emphasize how weak the signals that we're detecting are. And that is also the topic of the first homework question, is exploring exactly how little energy a radio telescope actually collects from the sky. So I think, few very promised last few slides. So coming back to the Jones matrices thing, so why this is useful is because every time you do an operation on a wave signal, you can just whack on another Jones matrix multiplication. So you can express your entire signal chain as every time you push it through a component, you just whack on another matrix. And so you end up with all these matrices, and then your entire system basically is just a product of matrices. And so the nice thing about this is you basically, some of these can be sort of known ahead of time, and some of them you have to calibrate for. So for example, the F array, the F Jones matrix is for Faraday rotation in the ionosphere, which we tend to ignore because it's not part of the telescope. So we treat that as an astrophysical problem. But parallactic angle, which is the difference between the orientation of your antenna and the orientation of the Earth, basically. So you can think about this as, think about a polarized source, a source with some polarization, rises, transits through zenith, and then sets, right? And so you can, from the Earth, from an observer's perspective, the polarization angle is changing over time. And so if you have an equatorial mounted telescope, it does the same thing, no problem. If you have an Altaz telescope, the telescope is moving like this. And so you can see the orientation of the telescope does not match the orientation on the sky. So that's this parallactic angle. And so you need to correct for that if you're observing over time. It's like the antenna frame of reference is not the same as the sky coordinate systems. You have a correction, that's purely geometric, so we can know that. And then you have the effects of the feed, the dish and the antenna modifies the signal, that's the C array. And then all the effects of the amplifiers and stuff, you just whack those into a single matrix, R. And so you can combine all these into a matrix product and then say, okay, some of these, like the receiver system, I don't know what these are, I need to solve for these in order to calibrate. And so calibration then becomes a problem of finding a small number of numbers in this matrix. And so you don't necessarily need to know where in the system a problem is happening. Like if you have something that's modifying the gain, you don't need to know, is it an amplifier or is it a bandwidth filter or is it something weird in something else? All you need to know is that between the beginning and the end, something is changing, you calibrate for that, you get the number out, you do the matrix multiplication. And so yeah, this is the sky signal, this is the measured signal. if you want to recover the sky signal, you just invert the matrix. So we know, this J is the system. What we really want to solve for is J inverse. If we find J inverse, multiply both sides by J inverse, you cancel out the system. This is your measurement. You take your inverse matrix, multiply by the measurement, you know what the sky was doing. So that's sort of the mathematical motivation for that. And this will get discussed a little bit next lecture, is the plan. I know that slide's big, but yeah, in sort of more practical terms about what's actually involved. I got through all of my slides.
Yay!
5 minutes over. Fine, we started 5 minutes late.
Started at U of T time.
We did. So, questions. I went through a lot really quickly. Yeah.
That's still in there. Well, I was going to ask where we really need accessibility. We really need it for the signal delay. I mean, but we have the interferometry and the other. What's
The phase array.
phase?
Yeah.
Yeah. So where is it for that?
Yeah. So the real power of an interferometer. Oh, sorry, Jessica.
Can you repeat the question, please?
All right. So question, and maybe I misinterpreted, so please correct me, is what is the distinction in when you would use an interferometer versus a phased array? Is that?
Oh, no.
No?
So,
Okay.
where we need aperture synthesis and what's the
Oh, so when do we need aperture synthesis? Yeah. So yeah, I mean, aperture synthesis, I think, is just another name for phased array. That's my interpretation. So yeah, I mean, the word aperture synthesis comes from the idea that with a phased array, you are creating a simulated dish. It comes back. Let me pull up the figure here. Where was it? It's further back. Yeah, it was this one. Yeah. So the word aperture synthesis comes from the idea of, you create the equivalent of your aperture, your dish, by having a lot of little antennas, or a lot of like little dishes, and you synthesize them by combining the signals electronically. And so by doing that is you have created the illusion of having a full-size dish and the full aperture, the full area of the dish, without actually having to make the dish. And so that's where the name comes from. I like to use the word phased array because I think it's more descriptive, because you're not necessarily, you don't also have to create a filled aperture. You don't have to stack all of the antennas right next to each other for this to work. You can space them out and you can do more complicated things. There's a lot more flexibility, and I think phased array is just a better term for what's going on. Yeah. Okay. So I've kept you guys over time. Thank you for that. So yeah, I am going to try and get the first homework question posted before next lecture. I'm going to post on Slack when that's ready. So please join the Slack. And yeah, otherwise, same time next week, and send me any feedback you have. Otherwise, next week we really dive into interferometry. And
Thanks, Cameron.
I'm scared like
Yep.
that was super informative. Thanks, Cameron.
Yeah, good. I'm going to stop the recording now.
Yeah, thanks. Bye.
Yeah, thanks. Bye.